Hello, Alok Agrawal with next video on course code ME501 internal combustion. So in last video, we have seen air standard cycle, its assumption, and Carnot cycle, which is considered to be a standard air standard cycle. Okay. So in this video, we will study Otto cycle, which on which spark ignition engine work, and diesel cycle on which compression ignition work. So let us start with Otto cycle. It is invented in the year 1876. It is also known as constant volume heat addition cycle, and spark ignition engine works on this cycle. Why it is called constant volume heat addition cycle? Because here the heat is added at constant volume when the piston is at TDC, top dead center. Actually, it is not the case, but in ideal condition, in air standard cycle, we consider that the heat is added during the process 2 to 3, and here we can see that the volume is constant, so we call it as a constant volume heat addition cycle. So this is the Otto cycle in PV diagram and TS diagram. In PV diagram, 1 to 2 is compression, 2 to 3 is constant volume heat addition, 3 to 4 is expansion. This is the power stroke. 3 to 4, this is the only stroke where we get power output or work output, and 4 to 1 is constant volume heat rejection. Similarly, when we plot this in TS, we get 1 to 2, that is isentropic compression, 2 to 3 is again constant volume heat addition, 3 to 4 is isentropic expansion, which is power stroke, where we get work output, and 4 to 1 is again constant volume heat rejection. So this is in PV and TS diagram. Let us start with the derivation of the cycle efficiency of Otto cycle. So here, first of all, 1 to 2 and 3 to 4 are adiabatic process in which no heat transfer takes place. The heat transfer are limited to the addition during 2 to 3 and rejection during 4 to 1. That is constant volume process. Now, what is the amount of heat added in this cycle? That is given by the rise in temperature when the heat is added. It's from 2 to 3. So heat is adding at constant volume. So heat added during process 2 to 3 can be evaluated as specific heat at constant volume multiplied by difference in temperature or rise in temperature. We consider that at point 2 the temperature of the working medium is T2, and at point 3 it is T3. So the rise in temperature is T3 minus T2, and we have considered this for a unit mass of charge or unit mass of working fluid. Similarly, the heat rejected during process 4 to 1 is given by Cv T4 minus T1. Okay, so this is the difference in temperature during the heat rejection. Means earlier the temperature is T4, and after rejecting the heat, the temperature reaches to T1. So what is work done? Means heat input minus heat output. So work done will be Cv T3 minus T2 minus Cv T4 minus T1. Now what is efficiency? Efficiency is output upon input. So here output is work done and input is heat supplied. So we can write efficiency as Cv T3 minus T2 minus Cv T4 minus T1 as work done, and Cv T3 minus T2 as heat supplied. So it can be written as when T3 minus T2, T3 minus T2, Cv will be cancelled out, and we can write it as 1 minus T4 minus T1 upon T3 minus T2. Now we know that compression ratio is V1 by V2, where V1 is the total volume of the combustion chamber when the piston is at bottom dead center, and V2 is the volume of the combustion chamber when the piston is at top dead center. Similarly, expansion ratio can be written as V4 by V3. So both compression ratio and expansion ratio for Otto cycle is same because heat is adding at constant volume and heat is rejecting at constant volume. Again, we are considering our medium as a perfect gas. So this ideal gas equation is followed here. You can implement this equation, that is PV is equal to MRT and PV to the power gamma is equal to constant. This both equation can be implemented here. Now considering process 1 to 2 and 3 to 4, because here 1 to 2 we are giving work input and 3 to 4 we are taking the work output. Now T2 by T1 can be written as V1 by V2 to the power gamma minus 1, and V1 by V2 we know that it is compression ratio R. Okay. Again, this T2 can be written as T1 into R to the power gamma minus 1. This T1 can be brought to the right hand side, and we can write it T2 is equal to T1 R to the power gamma minus. Similarly, T3 by T4 can be written as V4 by V3 to the power gamma minus 1. Again, T3 can be written in form of T4 r to the power gamma minus. So in this equation, we can replace this T2 by T1 and T3 by T4. Okay, so let us do that. Now I am writing in place of this T3, T4 r to the power gamma minus 1, and in the place of T2, T1 r to the power gamma minus 1. From denominator, this r to the power gamma minus 1 we can take common out. So what we get? 1 minus T4 by T1 upon T4 by T1 r to the power gamma minus 1, and this T4 minus T1 and T4 minus T1 will be cancelled out. So finally we get this efficiency as 1 minus 1 upon r to the power gamma minus 1. Okay. So here it can be seen that the efficiency is depend on the compression ratio of the engine. This R is a compression ratio and it is depending on the compression ratio only. Apart from that, it is not depending on any other parameter. And again, it can be seen that with increase in this R, the whole portion will decrease, and once this will decrease, the efficiency of the cycle increases. So it can be said that by increasing the compression ratio, the efficiency of the SI engine or auto cycle can be increased. So this is the derivation which is very important and can be asked in question paper, okay, in your exam. So this is about Otto cycle. Next is diesel cycle. Diesel cycle is also known as constant pressure heat addition cycle because here the heat addition takes place at constant pressure when the piston moves from top dead center to bottom dead center during the that process. Okay, this is again PV plot of diesel cycle and this is TS plot of diesel cycle. Almost these are similar to Otto cycle, but here the difference is only that in Otto cycle the heat addition taking place at constant volume, but here the heat addition is taking place at constant pressure. Again, this 1 to 2 is adiabatic compression and this 3 to 4 is adiabatic expansion. All the processes are reversible. 2 to 3 is constant pressure heat addition and 4 to 1 is constant volume heat rejection. Again, for calculating the efficiency, we have to know what is the amount of heat added during process 2 to 3, which is given by Cp T3 minus T2. Here, the heat is added at constant pressure, so we have to take specific heat at constant pressure. Again, heat is rejected at constant volume. We can write it as Cv T4 minus T1. So, what will be the next net work output? It will be heat added minus heat rejected. So, the work done will be written as Cp T3 minus T2 minus Cv T4 minus T. Now, next is efficiency. Again, we know that efficiency is output upon input. Okay. So, here output is work done and input is heat supplied. So, we can write like this. Now from here, this first term can be cancelled out when we separate it, but here Cv and here is Cp, so this will not be cancelled out. Okay, so it can be written as 1 minus T4 minus T1 upon gamma T3 minus T2 because Cp by Cv is gamma. The ratio of two specific heat is gamma. So here Cv by Cp can be written as 1 by gamma. Okay, now again what we have done earlier, we have to do the same thing. We can say that this PV is equal to MRT, ideal gas equation can be used here, and PV to the power gamma is equal to constant can be used here. Now considering process 1 to 2, we can write T2 by T1 upon is equal to V1 by V2 to the power gamma minus 1 that we have written earlier also, that is R to the power gamma minus 1. So T2 can be written as T1 R to the power gamma minus 1. Next, for process 2 to 3, 2 to 3 is constant pressure heat addition. So P2 is equal to P3. Okay, here we can see that P is equal to MRT. Okay, so P is constant here. So V by T is equal to MR by P. We can write it as this ideal gas equation as V by T is equal to MR by P. M is a constant, R is a constant, P is a constant. So V by T can be said as constant. So it can be written as V2 by T2 is equal to V3 by T3 for process 2 to 3, which is constant pressure heat addition process. From here, we can write T3 by T2 is equal to V3 by V2, and this V3 by V2 is called cutoff ratio. This is new term, cutoff ratio. Cutoff ratio means it is the volume, it is the distance or the volume covered by piston when before after the injection start and before the injection end. Means it is the duration of injection process when the fuel injector inject fuel inside the combustion chamber. V2 is the volume when it is started and V3 is the volume when the injection pressure or injection process stops. Okay, so this is called cutoff ratio. We cut off the injection process. Now it can be written as T3 can be written as T2 RC. Okay, and this T2 from here can be written as T1 R to the power gamma minus 1. So ultimately we can write this T3 as T1 R to the power gamma minus 1 into RC. Now considering process 3 to 4, we can write T4 by T3 as V3 by V4 to the power gamma minus 1. This V3 by V4 we can multiply and divide V2 in numerator and denominator inside this bracket. So we are doing that V3 by V2 into V2 by V4. Now see, this V3 by V2 is compression ratio that we have seen just here. This V2 and V4 can be written as V1 because V4 and V1 are same as heat is rejected at constant volume. So it can be written as V2 by V1. V1 by V2 is compression ratio. So V2 by V1 can be written as 1 by R. So this T4 can be written as T3 RC by R to the power gamma minus 1. Okay. So from here, this T3, we have just seen that T3 is T1 R to the power gamma minus 1 into RC. So replacing this T3 from here, we can write T4 as in terms of T1, that is T1 is equal to R to the power gamma minus 1 RC in bracket RC upon R gamma minus 1. Once we will open this bracket, we will get T4 is equal to T1 RC to the power gamma minus 1 because R to the power gamma minus 1 here at denominator and R to the power gamma minus 1 at numerator will cancel each other and we get like this. Now we can substitute all the values of T2, T3 and T4 in terms of T1 in this equation, and when we solve this we will get efficiency of diesel engine as 1 minus 1 on R to the power gamma minus 1 and like this. Now you can see that the first part of this derivation is similar to that of efficiency of Otto cycle and we get this here some extra term. So we can say that the efficiency of diesel engine is not only depend on the compression ratio but also depend on the cutoff ratio. And this is the derivation which is very important and can be asked in your exam. Okay, thank you very much.